Welcome, everybody. I'm going to be talking about evolving a library that has a combination of futures, promises, and actors. Got quite a few slides, but I'm happy to take questions during the presentation. Just go ahead and raise your hand, stop, ask questions. If I'm running low on time, then I might hold the questions till the end. But otherwise, please ask questions as we go. Quick intro. I've had a past life at UC Berkeley as a graduate student. I was at Twitter for many years. I ended up co-founding a company, Mesosphere. Did a lot of things in the container space. Currently, I'm back doing research at UC Berkeley, as well as working on a new venture called Reboot Dev. And a lot of the ideas I'm going to be talking about are baked into some of the stuff that we're doing at Reboot. So if any of this sounds interesting to you, please come talk to me afterwards. Big thanks to Nikita, Zakar, and Artur, who've played a big role in helping to build out the library I'm going to be talking about today. Okay. All right, so here's the chapters. First, I'm going to motivate futures, promises, and actors. Spend a handful of slides on that. I'm going to talk about this library that we built circa 2009 called The Process, which included those two things. Then we're going to talk about more recently when we revisited using the process and some of the issues that we'd had with it and actually deploying it at large scale. Talk about the evolution of that, the library we ultimately created from that we call eventuals. Talk about something that's near and dear to my heart that I've done research on for a long time around scheduling of these things. Talk about streams, which is a continuation of the eventuals idea. And then finally, some practical concerns, in particular type erasure in the library. Okay, so let's just jump in with motivating futures. All right. So one of the key challenges that we've faced when trying to build distributed systems with good performance and correctness, there's two key challenges that I really want to talk about. And when I was first putting this slide together, personally for me, because of all the software that I write, these are just my challenges building systems. And I think for a lot of people, it's just the challenges that we have building systems. There's really just two big ones. The first one is that when we're writing systems, we have to wait. And I'm going to talk about what I mean by that in just a little bit. And the second one is that we have state. There's not really anything we can do about it. So what do I mean by we have to wait? I'm going to use this as a motivating example throughout the presentation. Imagine that we've got some text. We want to spell check the text. And then after we've spell checked the text, we want to grammar check the text. One of the other things that's going to be pretty fundamental as I talk through all this that I care a lot about is functional composition, function composition. It's one of the tenets of how we program that helps us build big, large-scale systems. And so really what we're trying to do here is we're trying to spell check some text and then grammar check, okay? So getting back to this motivating example, when we look at what seems so simple, so harmless, just trying to spell check and grammar check, and we dig in a little bit deeper, we find this pesky little call in here, HTTP post, right? And all of a sudden, what seemed like a harmless function call to do spell check is not so harmless anymore because I'm going to have to wait for that call, right? That's some HTTP call. It's going to be going across the network. Maybe it's going across the world. Who knows? And whether you end up writing code that's blocking or non-blocking, which I think is a bit of a red herring when we think about those terms, the bottom line is you have to wait. You need the result of that data in order to grammar check. So it doesn't matter how you write your code. Fundamentally, you're going to have to wait. We have to wait. We can't get around it. We're going to have to wait. Okay? Now, there's many possible solutions. The first one's, well, we could just wait. We could just write our code that just waits, which I hope I don't have to defend that that's really only acceptable for introductory computer science classes. But for large-scale systems like most of us are building and that I've built in the past, that's really not an option. So there's a second option, which is use threads, right? This is a standard option for all these things. We might have to wait. We can just create threads. But again, as I think we've seen over the last couple of decades, that's just too expensive. And it's not conducive to correctness, which I'll talk a little bit about later. We can use coroutines. The word wait is right in there, right? Awaitables and coroutines, the word wait is right in there. That's what you're having to deal with is waiting. But when we were first building this library, this was circa 2009. This was actually pre-C++ 11. So it was a long time ago. We could use a different language, but Well, what would be the fun in that? I mean, there's lots of fun. We could use something like Erlang, which takes this kind of stuff as a core part of how it's built, having to wait. Or we could bring Erlang to C++, which is actually ultimately what we did, and we'll talk a bit about that. We could use callbacks, which many of you that have built high-performance systems that have to wait, this is probably how you've done it. You've used callbacks to say the continuation of what to do after you've waited. And I'm going to come back to this one, but I think a lot of you have built those systems and seen that they can be pretty brittle, especially when it comes to function composition. So I'm going to come back to this one because we're going to revisit it in a big way later. Or you could use this thing called futures promises. And that's what we ultimately decided, and I'm going to talk a bit more about them. But I wanted to first just pause and just ask, how many people have used futures promises? And then keep your hands up if you have used them in production, like you actually built in a system that's used in production. Okay, cool. So I'll be a little bit quick then about some of these futures promises background. The way I like to describe futures promises is they're kind of like a buffered channel where you only ever get to write one thing. Okay, so you can think of futures promises as kind of like a channel where you've got one thread that's got the read side of the channel, their reader, and then when they want to get something out and they call read, they block. And you've got some other thread that's got the write side of the channel. And when it wants to get something out, or sorry, when it wants to put something in, it calls write, and then it closes, because it only ever writes one thing. Okay, but in futures promises worlds, instead of a channel, we've got a promise. Instead of readers, we've got a future. That's the read end of the channel. Instead of read, we call get. On the write side, we don't have to have a writer. The promise basically is the writer. And instead of write and close, we just call set. The key important part here, though, is that in this sort of buffered channel mentality, on the read side, you're going to block when you want the data. And on the write side, hopefully, you're non-blocking. We're going to talk about why on the right side blocking can be a pain in the butt. Okay, so getting back to our example, how would we transform our example using future promises? Well, we'd go ahead and instead of returning a stood string, we'd return a future. Sorry, one quick thing. I'm not using C++11's stood future, stood promise in here. You'll see why in just a second. But also when we first built this library, it was circa 2009 and they didn't yet exist. So we built something else we planned on replacing, but we never replaced it, and you'll see why in just a little bit. Okay, so instead of a string, we'll return a future string. And instead of returning a body, we're actually going to grab a promise. We're going to get one of these channels. We're going to grab a promise. We're going to get the read end of future. We're going to return that read end for people to possibly use later. And we're going to replace our blocking synchronous HT post call with an asynchronous version of it that takes a callback. That's the lambda down there. Where we're going to move the write end, the promise in, and ultimately when the asynchronous HTTP call has completed, we're going to set the promise. Okay? This is the pretty standard transformation into using futures and promises. Okay. One of the really nice things about futures and promises is because we've got this extra abstraction, this thing that we're writing to, we can really nicely capture things like failures. So we can have multiple channels, if you will, not just for writing results, but also for writing failures. So I can not just call promise.set, but I can also call promise.fail. And you can imagine on the other end, on the future end, we're able to get out of it either the success or the failure. Okay? Not going to talk about too much detail there, but it's an important point. Okay. One of the reasons why, of all those things on that list that I talked about earlier, futures and promises were most interesting to us is because they enabled us to do function composition in a really easy way. Remember I said earlier, ultimately the goal of the code that I'm writing was to SpellCheck, then GrammarCheck. And that first little bit of code that I wrote was really simple, right? It was just GrammarCheck, the spell check of the text. That's ultimately what we're going for. That's one of the things that in our experience, being able to compose software as easy as that has led us to be able to build really large scale, easy to reason about systems. Okay? So what does that look like in the futures promise world? Well, we can do the .get that we talked about to actually get out the value in order to use it for the next thing we're trying to do. But of course, that blocks, right? And if the whole point of this was to not wait, but have a system where we wouldn't be waiting, where we wouldn't be blocking, then we need something else. You can imagine, maybe this isn't a big deal if you were just on, say, the main thread and this was all your program was doing. Sure, maybe blocking's not such a big deal here. But if this itself was some function that lots of people were calling, then it would be a much bigger deal if all of a sudden you're going to block in the middle of someone's function, in the middle of someone's function call. Okay, so instead, what can we do? Well, we can say, all right, yep, let's have this entire function also return a future. And let's replace this .get call with returning, composing, doing SpellCheck with .then. Okay, so what is .then? .then is basically a function on a future that lets us compose, where when that promise gets satisfied, it will invoke the function, the continuation that it wants to execute next. Okay? Have people seen .then? When the people that raise their hands around futures and promises, raise your hand if you've seen .then. Yeah, okay, good. Have you used something like it in C++ or outside? Okay. So C++ as standard doesn't have .then. And it's been one of the I think, contention points, and it's one of the reasons why most of the time when I ask people if they've used stood future or stood promise from C++ in production, they lower their hands because there's no great way to compose with futures and promises in C++. .then doesn't exist. And it's one of the reasons why we ended up continuing to use our futures and promises implementation in our library. Okay. One minor point. GrammarCheck in this case, I haven't actually shown you the implementation, but it can either return a future or it can just return a T. So the then can be smart enough to know whether or not there's more waiting that has to happen or not. Okay. All right, great. Okay, so that's kind of great. That's solving how we have to wait. That's helping us not have to deal with waiting. That's great. So let's move on to the second problem, which is you have state. All right. So to talk about state, first we should talk about what it means to execute code with futures and promises. So one of the cool things about writing software in this way is you only need a single thread to execute your code with futures and promises, because you never block. The whole point was finding all those places where the code would block and turn it into returning futures, setting promises later, so the code never blocks, so you only ever need a single thread. And in fact, there's many, many systems out there that do exactly this. They basically have some kind of an event loop thread, single thread. They use futures and promises. They use that thread for doing all execution. Okay? What's key to understand about that, though, is that the code that you're executing in between, say, SpellCheck and GrammarCheck might not execute atomically, because now it's going to get interleaved with other code that's being executed because you're waiting. When you wait at some point, when you make the HTTP post call, that event loop thread's going to execute other things, and so other things are going to execute in between the code that you're running, so it's not going to execute atomically, okay? And again, executing other code's the whole point to this, right? Otherwise, we would have just picked that original thing I'd crossed out that said, well, just wait, right? That's the whole point. We can't just wait, all right? This is what a lot of people call concurrency. This is kind of the fundamental thing people call concurrency. I have a single thread, but yet I'm doing a bunch of things simultaneously. I'm doing a bunch of things concurrently, and they differentiate it from parallelism because you're not actually doing anything simultaneously. You only still have a single thread. So if you've heard people differentiate the term concurrency from parallelism, this is often where it comes from. I think it's kind of a big red herring, honestly, because just because you're concurrent and not parallel, you still have all the synchronization problems that you have with parallelism. I'm sure we can debate that maybe you have strictly less because there's well-known wait points, but that's getting into minutia at that point. And of course, most of these systems don't just use a single event thread, they actually use a thread pool to execute all these futures and promises instead of a single thread, in which case you are running things in parallel. But I think what's most important here is that bottom line, once we've decided, all right, we're going to use something like futures promises or any system where we're going to be trying to doing things multiple things simultaneously, is you have synchronization problems. And you have to solve those. You've got some state and you've got some synchronization problems, okay? So there's many, many possible solutions. I'm not going to go through all these possible solutions, but there's been solutions that have been developed over the years. It was kind of interesting in putting this together. There's not as many great solutions that I really know about in, say, the last decade or so, but I think maybe there should be. When you look at these solutions, though, things like mutexes and semaphores, actors, monitors, one thing really stood out to me when we were first taking a step back and trying to figure out what we wanted to use to solve this problem. I mean, that's that you can really divide the solutions into two different parts, into either those solutions that assume you're using threads and those solutions that assume you're without threads. Okay? So what does that even mean? What does it mean, a solution without threads, right? So the solutions without threads, they're abstractions that encapsulate the execution model or semantics and the synchronization and the state. When you think about threads, threads are just kind of defining the execution model. Then you need other things coupled with those threads to deal with synchronization, mutexes or semaphores. You need yet other things to deal with the encapsulation of state, i.e. objects or classes. So we've got a bunch of different things that we kind of throw all together to solve this problem. A lot of these other abstractions, things like actors, they encapsulate it all together. The best way I have for describing the value of an actor is it encapsulates all of execution, synchronization, and state into a single entity. Okay? And usually when you have more encapsulation of things, it leads to higher level abstractions, which is what we oftentimes think of actors are, these higher level abstractions. And usually higher level abstractions are easier to reason about. Usually it means they're easier to run on more hardware platforms. Why? Because being at that higher level abstraction, we've got more wiggle room about figuring out how to map them to other hardware platforms. And they're usually easier to optimize because being at a higher level abstraction, there's more that we can do under the covers. Okay? So, you know, again, motivating why something like actors would be a good thing to use. All right, so in a nutshell, what are actors? Actors are some kind of local mutable state, kind of like an object. They've got a queue of incoming messages. I'll describe why I put messages in quote in a second. They receive and handle messages one at a time. Okay, and they send messages to other actors in a non-blocking way. It's not blocking to send a message. And it's the same programming model whether you're local or distributed, which is a huge win when you're building distributed systems. It's nice to not have to think differently when you're trying to put these things together. Now, you still have to sometimes think differently because communicating over a network is clearly very, very different than communicating locally. Oops. Not sure why that happened, but let's, okay, go back to this slide. There's a poltergeist in my computer. Okay. Okay. All right. Okay. So what do actors look like in C++? Most of the actor libraries that were created, especially up until about 2009, they were based on this low-level message passing send-receive loop. Okay, so oftentimes you had some kind of an object you inherited from some actor-like class, and then you implemented the receive function, which implemented the receive loop. That got a sender who was sending you messages. It got the actual message that was sent to you and some kind of arguments. And then it was your responsibility to, based on that message, decide what you would do with it. So you say, okay, this is this. I'm going to process this way. I'm going to treat the arguments in whatever way, so forth and so on. And when you wanted to send a message back, you would use the send function, which again does not wait. It's non-blocking. Okay? And the receive loop would process one message at a time. It would just keep getting called for each message that you were given. Okay? So one way to visualize actors is you can imagine that there's some actor B that's running. It's finishing up some operation, the blue operation, and actor C has sent a request for it to do something, the green operation. Once the blue operation is done, actor B can go ahead and it can execute that operation. While that operation is being executed, a second request might come in, but again, only one request is processed at a time. So that second request ends up having to wait. Okay? Until the green operation has completed, a response has been sent back out, then the purple operation can start and when it completes, it gets sent back out, okay? So that's basically actors in a nutshell. Message come in, only one message is processed at a time, okay? Only one operation at a time, okay? Yeah?
What are A and C doing while they're between request and response?
They might be, so the question is, what are A and C doing during these things? They might be, so again, send was non-blocking, so they probably sent, and then they went back into their receive loop to process whatever other messages they have internally. Great question, thank you. Okay, yep.
So can actor B process the message in parallel?
In parallel, could it process the message in parallel? Yes. So the default model of actors is you're gonna process one message at a time. If inside your actor you choose to process that message by doing more things in parallel, you totally could, but the receive loop is just gonna be one thing at a time, okay? Yep. Are the actors reentrant? I'm going to come back to that because I'm going to talk a bit about what that might look like when actors themselves need to block, which is to say in the middle of some actor operation, it might want to block to do something that takes a long time. Okay? Okay. All right. So I get this question all the time when I talk about actors. And again, actors were a key part of the old library and the new library, which is, can't I just get the same thing if I use locks for all my methods? Right? Can I just put locks around every single method and ultimately get exactly the same thing? I process one thing at a time. Or in Java, if I just put synchronized on every method. And the answer is no, at least not without doing a bunch of other work. And so to visualize that, imagine that instead of actors, we had threads. What does this look like in the thread-based world? Well, you can imagine thread B is finishing some operation on some object. Now, threads and objects have nothing to do with one another, right? So thread B is finishing some operation on some object. The object is where the encapsulation of the operations and the state is. So when thread B finishes that operation, the blue operation, thread C, or while it's operating, thread C might have actually said, hey, I'd like to actually do some processing on this object. I'd like to acquire a lock so that I can do some processing on this object. Of course, it can't right now because thread B has the lock and is doing the operation. When it completes, though, and it unlocks, then thread C can go ahead and take over, and it can go ahead and do its processing. When it completes, before it completes, maybe another thread would like to do some processing on the object, so it calls lock. But it can't do anything because thread C has the lock. Until thread C unlocks, can thread A go ahead and execute, okay? So ostensibly, we have here the same pattern of only blue, green, and purple being done one at a time, but the semantics are very, very different. I think this is the key takeaway that I want people to have when it comes to thinking about actors. If instead of thinking about these as threads, but actually the execution resources where these threads might have executed, the model of actors and threads tend to look very, very different. Instead of thinking about these as threads, if I think about these as CPUs, what tends to happen in many of these systems where you just put locks around your objects is your object, your data, actually bounces around between all your different CPUs. One thread executes some code. You have to pull in all the cache lines to operate on that object locally in that CPU. Another thread runs on a different CPU, gets the lock. You got to move everything to that CPU, so forth and so on. Contrast this, say, with actors, which is the typical implementation of actors, where actors are pinned to a CPU, and the data doesn't move. So you can get huge performance benefits. So listen, for parallel programs, often the data is going to have to move. That's the whole point of parallel programs, is I want to put the data in a bunch of different threads and have them execute. But for a lot of the work that we do for distributed and network services, the data is often not shared with other threads that need to do parallel work. The data is often shared with other computers. Bouncing the data around within a single computer is not really a good use of the resources. Keeping that data on a single core as much as you can provide huge, huge performance benefits. Check out the C* project, for example, of building some big, massive distributed systems in C++, using this actor paradigm. So actors, okay? All right. So that for us was our two big challenges. You have to wait and you have state, and we feel pretty good. We use things like futures and promises and actors, okay? All right, so now I want to transition into the next chapter, which is talking about the library that we built that actually implements these things. So this was circa 2009, okay? So again, this was before stood future promise. This was before lambdas. The library itself, libprocess, has evolved quite a bit. We built it actually to help build a distributed system called Apache Mesos at UC Berkeley. We chose at the time to use C++ to actually avoid a lot of the runtime non-determinism that we'd seen from a bunch of the other systems that we were doing research with, in particular Hadoop, which was on the JVM and had all sorts of garbage collection pauses, which were really, really painful. But we wanted to use actors. And so we ultimately built this actor library in C++, which is libprocess. And one of the things that we did, which was really interesting, was we combined futures and promises with actors. And at least for us, it was a novelty. We hadn't seen anybody really combining the two at a time. So I just wanted to take a couple minutes to talk about why actors need futures promises and why futures promises need actors, why they're a really, really nice marriage putting the two together, okay? So if we get back to this world, actors in C++, that I talked about earlier, when you think about what this code's actually doing, and I think the gentleman here asked a great question, which is what happens after an actor sends, say, a send from one actor to another actor? And I said, well, it goes on and does something else until it gets a response. That response that it gets has no locality to the send. There's no composition of the code between when it does a send and it gets a response, right? It's hard to reason about the control flow in these actors. What's happening here is I might be sending some response here, but the person that sent me the request, they've meanwhile have gone back in their event loop and they're doing a whole bunch of other things. And actors at this low level of send and receive loops, they're really hard to reason about. You know, sending and receiving messages is kind of like the assembly language of the actor level. And messengers are basically go-tos. That's what they are. They're go-tos in that switch statement, okay? Of course, we all know that go-tos are not a great idea. So how could we do better? Well, what we want is we want function composition, right? We want something like function calls. But of course, since we're working with actors, nothing can block. So rather than having our actors block, we'll have them return futures, okay? And of course, we want function composition. So we'll just use then. So how can we transform our actors? Well, we can take our actor, and we can change it, sorry, not transform. So how might actors end up looking like, okay? So we can imagine that we've got our actor, and again, it extends from actor, but now we can imagine we just have some foo function, and this foo function is going to return a future instead of a response. And the way that we execute this message, this is why I called messages, I put message in quotes, okay? The way we execute this message is effectively do the foo operation, whatever that is we'll actually call this special function that we call on, which we get from our actor parent, okay? And what on lets us do is it effectively lets us enqueue the execution of this lambda in that mailbox, in that queue of incoming messages that I talked about actors having before, okay? So actors are as simple as, we'll go ahead and we'll do this on thing. We'll say on ourselves. We'll execute this lambda when we get to it based on the entire queue, okay? Okay, and of course, within these calls, we might need to do something else that blocks. So this is the question about our actor's reentrant. Within an actor, when it's actually executing one of its message, it might need to wait. It might need to call something else where it wants to do something else. And it's totally fine. It can go ahead and can call another actor or can call another function. It can call anything else that returns a future, and we'll just compose. We'll go ahead and we'll compose whatever that thing's doing with the next thing. And within the callback, I don't have it here in the slide, but within the callback for this then, I just have a lambda, but there's no reason why I couldn't have in this lambda another on, which would effectively say implement the continuation of doing this stuff back on this actor, i.e. queue up the next thing I want to do as another message back on this actor that I'll execute later, okay? Okay, all right, so actors, pretty low level, futures and promises, a nice abstraction to combine with them, all right? Why futures promises need actors, okay? So if instead of actors, we had something like this, we got some struct object, and we had some function, some member, and it was returning some future. We have to ask this really pretty fundamental question, which I think is one of the reasons why then hasn't made it into the standard C++, is we have to ask a fundamental question about how then, the semantics of then with respect to where the lambda that you attach in a then should get executed. Okay? So again, some function could be some call to who knows where. There's some promise out there that when that promise gets set, satisfies it so that you can go ahead and you can execute this lambda. And the question is where should this lambda be run? Okay, so let's start with a straw man. We can imagine that whatever execution resource is completing the promise that's associated with this sum function, it can be the thing that executes the lambda. That seems simple enough, right? When I go ahead and I call promise.set, I will also go ahead and I will execute whatever lambdas have been chained to that promise function pair at that point in time, okay? But what happens if my then lambda starts looking like this? Now inside the lambda, I am actually trying to acquire some lock so I can increment some value, right? Now what's happening? Like, ouch, that hurts. Now basically some other piece of code that happens to be calling promise set and knows absolutely nothing about this piece of code is going to block. It's going to wait. Mutexes are perhaps the biggest offenders of you have to wait in your code base, not just calling HTTP calls or anything else, but mutexes themselves, okay? And this is extremely hard to reason about. The performance characteristics of this are really, really hard to reason about. I would argue it's almost akin to a non-deterministic garbage collector kicking on and doing some work. You know, we're executing in C++ so that we can get this determinism. We don't want, sometimes when we call promise.set, to all sorts of random things have to happen because I'm executing all these lambdas and I'm blocking, and other times when I call promise.set, nothing are to happen. And again, if I get back to that buffered channel example that I talked about before, the mental model that a lot of people have with promises and futures is that promise.set is non-blocking. It's not blocking. I get to set the promise and go on my way and do everything else that I want to do. Okay? Okay, so what are some solutions? Well, we could have an asynchronous mutex, which feels pretty good because now, at least when some functions promise is set and I execute this lambda, if I can't immediately acquire the mutex, then I'm not going to block the promise.set. So it seems pretty good, but the devil's in the details when it comes to release. Because the real question is what are we going to do when we call release? At some point, we're still going to have to execute those lambdas because releasing is going to mean that whoever queued up on this mutex.acquire on this then, now they're going to get executed. So maybe then I block and I call a bunch of lambdas. Okay? So we had a really, really nice solve with actors. We've got a great solve with actors. I mean, effectively what we want to do is we want to queue up the execution of these lambdas someplace else so that we don't have to do it right now, so we don't block. Yep, question?
I've never heard of an asynchronous mutex. What do you mean by that?
Okay, so an asynchronous mutex would be a mutex where, sorry, the question is what's an asynchronous mutex? Okay, so an asynchronous mutex would be a mutex where rather than when I go to acquire it, blocking the thread or you know, whatever execution resource I'm using until I can acquire, you know, suspending it into the kernel. Instead, what I'm going to do is I'm going to have it return a future. And I'm going to compose it with the rest of my futures and promises in the same way that anything else that would have possibly had to wait.
And that future holds lock because it got it.
Exactly, yeah, exactly. Okay? And again, the details are in the release. The release is still the thing that's going to act as that trickiest part. Yep, question.
I just have a general question about the future design here. Like, one problem with like that kind of composition is like there's like a race before like if the operation finishes before I can call then on the future. Like for instance, I'm gonna talk about exactly that point in a couple slides. Well, let me come to it. That race is really, really important for the evolution of the library. Okay? Okay. All right. So we had a really, really nice solve for this with actors. Rather than something like an asynchronous mutex or anything like that, rather we could just do this. We could say, all right, sure, when you call promise.set, we'll go ahead and we'll execute all those lambdas because that's just what we'll do. But we'll try to be as good as we can where when we execute those lambdas, rather than calling things like acquiring locks or using asynchronous mutex or anything else like that, we'll just enqueue the execution of what we want to do back on our actor. That's non-blocking because I just get to enqueue up, run this lambda at some later point in time, and then I just get to continue to go.
Okay, so it was a really, really nice marriage to put these two things together so that we wouldn't have futures or promises that would block anywhere. Okay, this is kind of cumbersome, writing, you know, a lambda with an on and then another lambda, and so we had an abstraction for it, which was basically just defer on. This is actually not the exact terms we used in the libprocess library, but I'm trying to pick some, if you go look at that code base, I'm trying to pick some terms that are a little bit more, that are not from 2009, so it might make a bit more sense. But anyway, we can abstract all that into just a defer on. Okay, so basically the actor is providing the executor to execute the continuation. Okay, it's providing the execution resource that they need. Setting the promise is fast again. It's non-blocking. Whoever the promise associated with some function is, yes, it goes ahead and it executes all the lambdas associated with the future, but they just enqueue things up on actors' message queues, and so they're really, really fast, at least faster. Okay? And again, there's no need for synchronization here. We didn't need locks, we didn't need mutexes, we didn't need any of that, at least in the user level code, because we get to take advantage of the actor execution semantics, which is only one message is going to get processed at a time. Okay, all right, cool. So we used the process to build Apache Mesos. GitHub says it's about 750,000 lines of code. We had hundreds of contributors contributing to this project, and I counted, and there's probably about a dozen mutexes in the entire system. And almost all those mutexes are for interfacing with code outside of libprocess. So, you know, the proof point I'm trying to make is we're able to build this system up to massive scale, clusters of 80,000 machines, and we didn't have to use locks. We got to use actors and futures promises. Okay? All right. The next chapter, revisiting the problem. Okay. So if we come back to where we all started, I know there's been a ton already, but if we come back to where we all started, all we were trying to do at the end of the day was basically compose SpellCheck and GrammarCheck. And when you look at this code, one of the things you notice about it is the code's sequential, right? I got to do one thing and then the next thing, right? It's definitely not parallel. It's not even like, if you executed it concurrently, there's not even any state to synchronize. Like, you know, sure, by all means, you could execute this concurrently, but like, I will never have to do any fun things to deal with. Like, I don't care that it's not executed atomically. It doesn't matter, right? And yet, our solution to the problem using futures, promises and futures, had to acquire tons of locks and dynamically allocate a ton of memories under the covers. Okay, so again, I just said that we built an entire system where we only had about a dozen mutexes, but under the covers, within the library itself, we were acquiring locks and dynamically allocating memory all over the place. All right? And that might be fine for parallel and concurrent code, but for simple code like this, it seems really unfortunate that we have to do that, right? So why do we need locks and dynamic memory for futures and promises? This gets to your question, which is effectively the race that's occurring. So let's talk about it. So if I were to take this code and I were to just say, okay, I'm going to inline SpellCheck. We've all looked at the SpellCheck function. I'm going to inline the SpellCheck function. What does that do? Well, I've omitted some stuff, but basically I've got my promise and future, and I've got my async post function. And within that, I'm calling promise.set. And from the future I get back, I'm doing a .then to ultimately do the grammar check, the next step in this sequential sequence. There's a race. There's a race between promise.set being called and future.then being called. Why is that? Because by calling async post and passing this this lambda, this callback, that callback might be executed by who knows what, by some event loop, by some other threads, by however async post is implementing their code. Okay, and so they might be on one thread calling promise.set, while meanwhile, we're on the thread that originally called async post trying to call future.then. Okay, so there's a race. So the promise may be set at the same time that the continuation is being composed via then. So we need locks. We need locks to deal with that race, so that not two people are trying to modify this thing at the same time. The promise may also be set before the continuation is composed with then. So we need to dynamically allocate memory too, because we got to have this buffer. Remember I said it was a buffer channel. We got to have this buffer where we can actually write the data to. Okay? So the big question that we asked ourselves, because we had this code all over the place. We had tons of code that literally was just a bunch of sequential steps that, if you wrote it in your CS 101 class, it would just be do this, then do this. There's no concurrency, there's no parallelism, there's nothing else. And all these steps ended up having to acquire tons of locks and dynamically allocate memory. So we said, can we avoid locking and can we avoid dynamic allocation? And that led to the evolution of the library. Okay. So one of the first intuitions that we had when we wanted to evolve this is we kind of looked at the old code and we said, well, where does the locking occur? And the locking occurs inside the promise. It doesn't occur when we execute the callback. When some other part of the code actually executes the callback, there's no locking there. I've given them the callback, they can go execute the callback. So callbacks is this really, really interesting model where, hey, if I can give you the callback or the continuation to execute next at the time of the call, I don't need any locking. You can just go ahead and you can call that thing. So that was kind of our first thought for, hey, can we avoid locking? Well, what if we just try to go back to using callbacks everywhere? So we said, yeah, let's throw away all this stuff. Let's just go back to using callbacks everywhere. So imagine that, we're going to rewrite SpellCheck to take some function, some callback. We're going to throw away our promises. We're going to actually go ahead and we're going to, within that callback, just go ahead and call F. And that's going to be the continuation that we want to do next. Great, so we can invoke continuation without locks. But maybe, we don't want to pass through out-of-stood function, so we're going to have SpellCheck actually take in some arbitrary thing we can call. We'll call it K, because for whatever reason, when I first learned about continuations in college, they always seem to use the letter K to talk about the continuation instead of C, so K everywhere is representing continuation. So we'll take some K, the continuation, we'll go ahead and we'll invoke that. Okay. So this is interesting. Okay, so I can just get back to the good old world that maybe many of you have built asynchronous concurrent systems with before, which is callbacks. Callbacks don't have locks. That's kind of nice. But first, futures promises, they had a lot more than just invoking the callback. They also had the concept of being able to deal with failures. Remember, I briefly mentioned that earlier. Okay, so what if I actually wanted to not just call the callback, but I actually wanted to have both a success path and a failure path? Well, okay, all right, so I can go ahead and I can take SpellCheck and I can have a success callback or a success callable that I'll give and a failure callable that I'll give, and then I can figure out within the body how I'm going to implement that. Starts to get pretty untenable passing all these callbacks all over the place, right? But we kind of liked the direction we were going, so we said, all right, let's just go ahead and let's actually make that all be part of this K continuation. And rather than just calling K, we'll actually have functions we can call in K. We can either call k.fail, or we can call k.success. And we'll have this continuation that gets passed in. If we want to go down the failure path, we'll call fail. And if we want to go down the success path, we'll call success. Okay? Okay. I'm not going to be discussing cancellation and canceled in detail here, but there's another path that you need to consider as well, which is also just what happens when you want to cancel things or things are canceled. And there's basically, you can imagine there's a k.canceled call in here as well. Okay? So this starts to look kind of interesting, like, hey, maybe if we just go back to composing all these Ks, we can kind of get what we had with futures and we can avoid locking. Maybe none of you like having to pass callbacks around, but we'll get to that. Okay? But we still have this whole memory thing. So we come back to this and we say, hey, how do we deal with memory? So the first question is, are we actually allocating memory in this model? And the answer is we are, because if we dig down into async post, this is async post now. If we dig down, under the covers, it's probably calling something. I have it calling this HTTP post function, where ultimately it's passing in some function pointer, where through that function pointer, it's ultimately passing some type erased void star data that represents what I'm trying to do next, okay? So yeah, in this model, at some point I got to allocate memory for the thing I'm going to do next, for that next continuation. All right, so yeah, I got to allocate the continuation somewhere. That's what's going on. Okay, so we kind of looked at this and thought to ourselves, okay, that's unfortunate. It'd be nice if we didn't have to actually do the memory allocation. And you solve all problems in computer science with a level of indirection, and at some point we got the idea, well, we could probably avoid the allocation if we returned the continuation k that we passed in as part of the result of the function. Like right now we're returning void. Maybe we could somehow actually make k be the thing we're going to return, and then maybe we won't have to allocate. So we could take a continuation as argument, and we could also return a continuation as the result. And that continuation that we return can compose or encapsulate the continuation that was passed in as an argument. Okay, so what would that look like? So we'll take post, okay, and rather than having to do this dynamic memory allocation, we'll create this object, this structure that we'll call our continuation. That's going to have a start function or a success function, okay? And rather than having to delete k, allocate this k thing, we'll actually have passed k in, okay? And rather than returning void, having this entire function returning void, we'll have it return whatever type this whole struct continuation maps to. And this entire post function will basically return a continuation that moves in the URL in the body and the actual continuation that was originally passed into me. Okay, so I'll take a continuation and I'll return from this entire thing another continuation. And by doing so, I haven't actually dynamically allocated any memory. What I've done, though, is I've gotten back this other continuation, which basically represents my computational graph that I want to execute. Okay? But the graph is lazy. I haven't actually started to execute anything yet because, right, I solved the problem at a level of indirection where I wrapped this whole stuff up into a continuation. I returned back to continuation. Now I just got this k. I'll take your question just a sec. Okay, so it's got to be explicitly started. We'll have to actually explicitly start this thing if we want any computation to occur. Okay? But the graph now, I can allocate the entire graph on the stack. Or if I wanted to, I can allocate it on the heap. But the nice thing is I could do a single heap allocation. I could allocate my entire computation graph that's represented by my chain of things that I want to do once. Okay? And of course, the big caveat here is memory's got to exist until the completion of this chain of things that I'm doing. Okay, yes, let me take the question.
Can you go back to the previous slide, I think? Yeah, so in this, where is the continuation actually being evaluated?
Yeah, so basically, this entire post, I'm passing in some continuation here, which is the next. This is k prime, and I'm getting back some continuation, which represents the entire chain. When I ultimately call k start, that kicks off this start function, which will then kick off the underlying asynchronous HTTP post, which has this k there. That's my actual continuation, which then will succeed once that HTTP post completes there. Cool. Okay, great. Okay, it's go-tos. It's all a bunch of go-tos. But the idea is at that layer, maybe we're acceptable with those go-tos because we can provide higher level abstractions on top. Okay? All right. Wow, we can avoid locking. We can avoid some dynamic allocation. So this led to the evolution of the library and to this new library we ended up creating that we called eventuals. Okay? So these continuations or these continuations in continuations, we kind of wanted to give a name to them. They're not futures promises or something else. For us, we called them eventuals. And we do actually have a GitHub project that you can check out. We're working on them there. Okay. Now, one of the things we didn't love was passing around the continuation k. In our experience, wasn't very ergonomic. It led to kind of an inverted control flow or control structure of the code. So we ultimately said, well, can we solve that problem too? And we did by creating this eventual type. Okay. So rather than passing in the continuation, and then having some continuation that we create ourselves in which return, you can actually return this eventual type. It kind of feels a bit like a promise. This is an eventual of an HTTP response. It takes the lambda that you're actually going to execute when this eventual gets started, okay? and what we pass to you is your continuation. Okay? Another way of saying this is basically a continuation passing style way of writing code, which a lot of people don't find to be an easy thing to do. So maybe we can abstract some of that and just kind of put the continuation K here. Okay? And so everything else basically looks exactly the same, where instead of basically us describing our continuations ourselves, we've got this nice helper object, this thing called eventual, which lets us basically construct what we want, where this K gets given to us at runtime when we're actually running. Okay? So what's the type of this thing? Like, who knows? This would not be a library that we'd be building before we could put an auto there, right? Because everything is really, really composed lazily. So what do I mean by that? Well, if we go back a higher level up, so this is the post function. So if we go higher level up, which was the SpellCheck function calling the post function, and we replace the future version with the eventuals version, okay, so instead of a future stood string, we're going to be returning an auto, because it's going to be this continuation type, okay? Instead of promises and futures, in this case, we just get to call HTTP post, because HTTP post is actually doing all the continuation magic under the covers. So our SpellCheck function becomes really, really, really simple, where all the magic is under the covers. What's really, really cool about this is our SpellCheck function basically looks identical to the synchronous version that I showed you in the original slide, but it's not blocking. You have to wait, but there's no blocking. Then on the other, so now we get even a layer above that, which again, the whole point of this was we wanted to not just do HTTP post and not just do SpellCheck of HTTP post, but to do GrammarCheck of SpellCheck, which is doing HTTP post under the cover. So what does that look like? Well, if we transform the future version, again, we're going to replace the future string with auto, and we're going to go ahead and still just call SpellCheck like we were, but instead of having .then on the future that we get back, we're going to compose it with another eventual combinator that we call then, okay? And in this case, originally we used to have a dot function, but ultimately we ended up using the pipe operator. We overloaded the pipe operator to compose these things. But you can think of this as basically this eventual type that I returned here, this thing, it knows how to compose with other continuations. Just like future knew how to compose with other continuations, it knows how to do that composition. And whatever it gets composed with later, whatever that thing is that comes later, in this case it's then, that's the type of that auto ref K that gets passed in at runtime. That's what that K is from the eventual. Yep, question?
A couple slides back, you showed how the function got really simple and beautiful. Right there. Would that still have been the case if you had to do 2 posts in that function?
Possibly, depending on whether or not what you need for, the question is what happens if I needed to do 2 posts? So in this case, the 1 post is nice because I don't have to depend on anything from the previous post to do something else. So if I needed to do something else, like another post, I could have done it like this, where I could have used the then combinator. It's also possible that HTTP post could have been written in a way, in this case it was, where you can just literally do pipe HTTP post, pipe HTTP post. And it'll just do the sequence of those things. But by doing that, the result of the first HTTP post is basically being thrown out. So if that's a side effecting function you're doing and you're composing in that way, that's totally fine. But if you need the result of that thing, you need something like the then combinator to actually get the data and work with it. Okay? Okay. All right, so in our experience, 90% of the time when you're writing code like this, you're sequencing or composing eventuals using combinators like then. Examples like this. Less than 10% of the time are you actually using the eventual. It's when you're actually working with the lower level systems that are doing the asynchronous stuff. So most of the time, you're never even working with a K. You don't even care about a K. You're just using thens and texts. The code looks almost identical to all the futures promises stuff that we were doing until you need to go under the covers and actually care about that K because, for example, you need to deal with the waiting. Right? This is where we're actually dealing with the waiting, and we're having to do all these funky casts because we're calling this function pointer thing and passing data as a void star. Okay, all right. I'm going to try to cruise through a couple more things because I've got at least one more really great thing I want to talk about. There's lots more accommodators than just then. There's let conditional raise. I'm not going to go into any detail on them. The entire thing is we actually have pulled in libuv into it. So we also have an event loop that's part of the library. So you've got things like timer, signal, domain name resolve, HTTP get, HTTP post, open file, read file. Again, it's meant to mimic the libprocess library that had all this stuff as well. Okay, so actors. So again, we did all this. We wanted to do actors. How did the actor part work? Well, what changes is, again, we replace the future with an auto. And rather than doing an on-self, we actually have this function that we call schedule. Okay, and the idea of schedule is it's basically returning an eventual that will ultimately schedule the execution of this lambda within that message queue, that mailbox that I talked about with the actors. Okay, all right, so scheduling. So we run into this really, really interesting situation that we ran into with futures promises as well, that we run into here, which is where should the continuation run? In particular, when my event loop is done doing HTTP post and it wants to call kSuccess, should it just call kSuccess? Should it use the same execution resource that it was using when it got to this place? It's the exact same problem that I had with promises that we were talking about earlier, okay? If it's using the event loop, like that's really unfortunate. That's probably not what we want. We want to get off the event loop, right? The whole point of the event loop is so it can process events. So if we keep executing a bunch of things in the event loop, that's no good. And if it's an actor, we also want to get off the actor, right? The whole point of the whole actor model is that we execute something in the actor, but then when we're executing code from some other actor, it's that actor that's going to execute that code, not us. Okay, so it raises this big question about where should the continuation run. And if we kind of go back to the original motivating example and we say, think about something like HTTP post, we're reminded that we've got this thing called function abstraction, right? And function abstraction is what enables us to separate the concerns of interface and implementation. Okay, and so if we kind of go back to like first principles and we say, we don't care how HTTP post is implemented. If it uses multiple threads, we don't care, nor do we need to. If it uses a GPU, we don't care. If it uses an FPGA or system on a chip, we don't care, right? On the flip side, if we had called HTTP post and computation when it continued happened to be on a different thread than when we called HTTP post, I think we'd probably be pretty surprised, right? We'd be like, whoa, that seems really, really weird. Or if we called HTTP post and computation continued on a GPU, but we started on a CPU, I think we'd probably be pretty surprised, right? I think that this would pretty much break the principle of least astonishment, okay? So what we did in Eventual is when we said where should the continuation run is we said we should use whatever execution resource we were using before we had to wait. So before we called something that ultimately got on the event loop, when we continue, we should continue using the execution resource that we were using before we had to wait, okay? If we don't do it that way, what we are running into is situations like this where let's say we wanted to run SpellCheck and GrammarCheck on a thread pool. We'd say, all right, great, we're going to execute this code. We're going to schedule it on a thread pool. Then we found ourselves having to do this. Okay, well, after SpellCheck returns, we're going to go get back on the thread pool. So why do we need to go get back on the thread pool? Well, because SpellCheck continues on the event loop. So we got to get off the event loop. I got to get back on the thread pool. So to be defensive as a programmer, I got to think every single time about getting off the previous computation and getting on this one. And of course, really what I should be doing is writing a great comment that explains why I have to be doing this every single time, which says, I'm rescheduling on the thread pool because we looked at the documentation of SpellCheck and it continues on the event loop. Or I'm rescheduling on the thread pool because I looked at the implementation of SpellCheck and it continues on the event loop. Or even worse, I'm rescheduling on thread pool because I emailed the developers of SpellCheck and they said they'll use the event loop in the future, which we don't want to be on, so we're being proactive now and doing this blah, blah, blah. Okay, so hopefully you get the point. Okay, I'm only dwelling on this because if I understand correctly, I think that this is an ongoing topic in one of the STUD execution proposals, and I think it's a really, really an interesting, important one. And I'm looking forward to hopefully Eric talking more about this in his talks here tomorrow about that. I also have a lot of history in the past working with hierarchies of schedules and dealing with some of those things. Okay, all right. I'm going to wrap up there. I didn't get to streams and type ratio, which is totally fine. What I'm going to do, though, is I'm just going to wrap up by just saying, to sum things up, at the end of the day, we have to wait and we have state. So be thoughtful about your approach. Futures and promisers are a good approach, but they have overhead. This idea of continuations and continuations, or lazy continuations, or eventuals, they can let you have your cake and eat it too. Actors are a good approach for state, but you need to consider scheduling. Function composition is fundamental. Any of the approaches that we build should do that. And function abstraction is fundamental. I don't think we should break the principle of least astonishment in whatever things we're trying to build. And yeah, that's what I have. Thanks.